Now notice that none of these operators commute with each other, which means that they are all incompatible with each other. For example, if an arbitrary component L sub I has definite value, then its commutator with L sub j is proportional to L sub k, but that's not 0, so therefore L sub j cannot have definite value if L sub I does. And likewise with L sub k. So if one of your components of the angular momentum has definite value, then the other two do not. This is in contrast to the linear momentum operator, where all three components of the momentum operator can have definite value because they all commute with one another. Angular momentum only has numerical value in one direction. Because of the symmetry of the equations, which one we choose is arbitrary. So we usually like to visualize an object sitting in the xy plane. And this here is the xy plane, rotating about the z-axis. So naturally, for this purposes, we want to talk about the z component of the angular momentum operator. Again, it's arbitrary, but this is just for formalism purposes, so we can get started. So, we want our z component of angular momentum, L sub z, to have definite value, which means that our state is an eigenstate of the LZ operator, L sub z operator. But what about the total angular momentum? The total angular momentum is the magnitude of the angular momentum vector divided by L squared equals Lx squared plus Ly squared plus Lz squared. And we'll use this form because now that these are promoted to operators, the square root of a sum of operators is pretty much nonsensical. So if we have a state with definite Lz, which is to say that it's an eigenstate of the Lz operator, then may it also have definite total angular momentum. In other words, is the commutator between L squared and L sub z equal to 0? If it's 0, then our answer is yes. We can have a state which is simultaneously an eigenfunction of, or an eigenstate of both L squared and Lz, which means that you can have a definite total angular momentum and a definite angular momentum in one of the directions, or in the z direction, for our case. And if it's not, then the answer is no. So we're going to compute the commutator between L squared and L sub z. Well, we've defined L squared as Lx squared plus Ly squared plus Lz squared, and commuted with L sub z. Well, we can break this into a sum. This is just 0 because that's just L sub z with itself when you break the commutator a. So that's just going to be 0. So now we need to figure out these terms. Well, we're going to break up the commutator, the product here. Lz, we're going to put Lx, L sub x on this side, and L sub x, L sub z, L sub x on this side, plus L sub y with Lz, plus L sub y, L sub y with L sub z, and Ly on this side. Well, from our commutation relations, we know that let's underline that. We know that Lx with Lz is just negative IH bar times Ly. Negative IH bar Lx Ly. Negative IH bar Ly Lx. And we know that Ly with Lz is IH bar Lx. So plus IH bar Ly Lx plus IH bar Lx Ly. That cancels, and that cancels, and we get 0. And we find that L squared does in fact commute with L sub z. And in fact, if you did this calculation with the other components, you find that it's also 0. So that means that our choice of L sub z, of singling out L sub z as special, is still arbitrary. So we have, I'm going to rewrite the commutation relations. L sub x with L sub y equals IH bar L sub z. L sub y, L sub z equals IH bar Lx. Lz with Lx is IH bar Ly. So, in our system, we want a state f, an eigenstate f, which is an eigenstate of Lz. And it's also an eigenstate f of the operator L squared, which, as we said, means that our state has definite total angular momentum and definite angular momentum in the z direction. Well, we can rewrite this equation. L sub x plus Lz squared f equals lambda f, and Lzf equals m times f. Well, when you square Lz, when you act on it again, that's just a constant, so it'll act on that directly, and it'll just be m squared f, so some constant times f. So we have Lx squared plus, we can subtract that off, Lx squared plus Ly squared f equals some constant times f. And our commutator, Lx with Ly, when it acts on f, is just IH bar Lz acting on f, which is just IH bar times m acting on f, which is just a constant times f. So we have two operators here, Lx and Ly, whose commutator for our purposes is constant. And the sum of their squares is an operator for which f is an eigenstate of. This is very similar and structurally to our harmonic oscillators problem, where we had the 1D position and momentum operator, x with p equals a constant, and omitting factors, their squares equals h bar, of which we wanted our state to be an eigenstate of. So our hope is that since we derived ladder operators in terms of x and p and solved our energy levels here, that we can similarly derive some ladder operators for out of Lx and Ly and solve our system that way, which we'll do in the next video.